super exciting conversation topic today. And so I guess to start out, my name's Matthew Schultz. I'm the CEO of Ocean Biotechnologies, and we develop genetic medicines for health and longevity. So our first program makes you build muscle without exercise. We're trying to use this to make old people strong. And we've developed tools that will kill damaged cells and try to reduce inflammation and enable the body to better repair itself. But I first got into the field of genetic medicine from computer science about 15 years ago. And I got in with this thesis that the essence of life is information, and if you can manipulate that, you can basically do anything. In fact, the first biotech I started was called ImmuSoft, and even the name's a portmanteau of immune system software. And back then we were trying to build an app store for the human body so that instead of making a drug and injecting it, you could basically program the patient's own cells to produce the therapies inside them. And back then, there were no approved gene or cell therapies at all. So it was like definitely going out into the uncharted territory. And excitingly enough, today it's now the first engineered B-cell therapy to be going into human trials. And so we've been following this stuff for a long time. But like I said, today we're going to talk about a topic that is intimately familiar to all of us, and that's age, and particularly the decline that we encounter with it, and in ways that we might be able to mitigate it. And so we don't really have enough time to get into the more, say, academic hallmarks of aging. So I guess to frame things, we're going to talk about like aging in the context of progressive loss of function and accumulation of damage with time. And we're also not going to go so much into the cosmetic aspects of it, like makeup or something. Although I do think it's interesting to point out that an AI looking at a selfie is just about as good at predicting your biological age as an algorithm looking at a DNA methylation clock. And so, like, something that I guess is intuitively familiar to us is that you tend to, if you look worse, you probably are worse. I'm gonna make friends really early here. So we're gonna be talking about anti-aging, and so in this context, we're looking at things that could, either slow down these kind of losses, mitigate the damage, or even rebuild tissue or regain homeostasis functionally. And so we're gonna try to touch on this idea of biological immortality, and this is a bit different than what Ray Kurzweil was talking about for like escape velocity. I mean, we're talking here that we could eventually get good enough at these kinds of interventions that we could make the ravages of time effectively negligible, that you could make death elective, basically live in perfect health indefinitely. And it sounds odd, but if you kind of follow out the logic of these things, and you could do them, you wouldn't be 100 forever, you'd be 30 forever. You'd live in perfect health indefinitely. And one of the big challenges that we're faced with this is that humans are already incredibly long-lived. We live longer than virtually any other mammal out there. And I mean, there's things like trees, of course, that have been around since before Christ walked the earth, and reptiles and fungi. But those things are so different from us that it's hard to kind of implement those techniques in a human. There's one really interesting exception to this, though, and that's the bowhead whale. So this is a very long-lived mammal, lives at least 200 years old. So there's bowhead whales swimming around today that were swimming around when Thomas Jefferson was president. And so there is actually room for improvement here. There's also this, I think the most fascinating paradox in the space, that we are mortal humans, but we have an immortal germline. And so you can take an old sperm and an old egg, and you put them together, and in a matter of around 7 days, it's young again, it's 0 years old. All the damage of your life is reset back to zero. And this suggests something fascinating to me, that written into the code of life is a program to undo age. And so the question then becomes, can you control it? After all, I mean, we don't want to turn ourselves back into an embryo. But it does mean that there's a backup copy there. Somehow this super complex epigenetic landscape with 3 million or so CBG sites and methylation sites can be reset to this predictable state. It means there's a backup copy of it somewhere, and we can manipulate it. So it's a problem that we're trying to solve here. A lot of other people are trying to solve it. I mean, you may be familiar with even Altos launched with $3 billion, the largest Series A ever, to try to tackle this kind of reprogramming problem. But we need better tools to do this. And it's why if you look at my startups from Immusoft to Ocean, Sigma, Oncocenix, they all were focused on building tools to manipulate information in life. And it's what our panelists are also working on today. And so they're going to talk for a few minutes. I think we've got 10 minutes per panelist on what they're doing and the tools they're building and how they're applying them. And then we're going to have a panel discussion. And hopefully we'll have time for audience Q&A. So with that, let me welcome our first panelist coming in by Zoom. And her name is Vered Kaplan, and she has an engineering background, is the CEO of Orgenesis, a biotech portfolio company focused on making advanced therapies more accessible and available via a decentralized approach. She is actively involved in expanding a global network that aligns industry, academia, hospitals, and governments to standardize the production and supply of cell and gene therapies to achieve the goals of affordability and availability. Prior to coming to Orgenesis in 2014, Ms. Kaplan held a variety of entrepreneurial positions at various medical device and biotech companies for more than 2 decades. Please welcome Vered.
Thank you. So first of all, I'm so jealous of you all that you're over there and I couldn't come over. So at least I can get a chance to speak on the panel, and it's lovely to see all of you. And I hope you're having a wonderful, wonderful event. Bit about my background. My name's Vered. I am an engineer, mechanical, electronic, biomedical, lots of hardware, lots of software. And just as discussed before, this idea of cells being computational beings is something that has become really a big part of my career and my life. So over a decade ago, started the company by the name of Orgenesis. And our goal was to make cell and gene therapies available to everyone. Now, it's not always obvious to people, but the cells in our body, these little wonderful computational little beings, they actually have not only the ability to manufacture things, to produce everything we need in our body, they actually have their own code. And I know we'll talk about it a little bit, but that code is at so many levels. And I'd set up a company that its goal was to make these products. Now, a decade ago, there were maybe 10 products like this. Today, there's thousands out there. The level and ability of the scientific community to take cells in the body and really program them and make them do things that they should do is amazing. And started this company and doing, cancer treatments, diabetic treatment, taking this type of cell and really producing it high level, making sure you can get it to the patient. But one of the things that had really kind of been very sad that these capabilities to take a cell, reprogram it, do whatever you want it to do, including anti-aging, was so expensive and so difficult. So I actually set out and built a global network of kind of these mini computers, okay, or mini factories that enable reprogramming of cells. With this concept that no matter what we achieve scientifically, which is wonderful, should be available to everyone in the world. And one of the things that continuously comes up is this concept of, okay, we can do anti-aging. I mean, that's kind of my daily business, taking a cell, bringing it in, making it very young, reprogramming it again. We do it all over the world. We take immune cells, reprogramming them. We do all kinds of things. And when you look at what that, okay, what's aging? How are we going to live here forever if we want to? Well, there's a couple of things you need to do. First of all, one thing you want to really make sure that doesn't age, if you want to live a long, maybe eternal life, is your immune system. And we know today so much about reprogramming immune cells. There's so much know-how, and we're just beginning on how to teach an immune cell how to genetically modify it so it knows to attack specific targets, and also how to activate those mechanisms that make that immune cells younger again. Because many times when you're treating patients with a disease, the immune cells have aged a lot. So the knowledge is there. Another thing about you want to live forever, you better have the energy for that. And that's really, a kind of metabolic system. And again, teaching cells or enabling or programming cells to have that metabolic capability is something that is advancing at an incredible pace. So, okay, that's great. Let's say we can do it, right? Hopefully, and that's our goal in Orgenesis, to make sure we can do it everywhere and for everyone, not just for the, I don't know, million people who have an access of $1 million to get younger. But let's say we can do that. Okay, we can take this kind of immune production system, this amazing computational information storing system that's our body, and we can reprogram it again and again to stay young. That sounds wonderful. But when you think of this kind of in a more kind of conceptual basis, right? Okay, let's say I had that choice, and here I can pull that trigger, and I can find that secret switch that would make me live forever. So for me, I don't know. I mean, as I say, I don't have any inside information what happens after you die, but I'd give it a 50% chance that there's something going on, okay? Whether it's a beautiful heaven or reincarnation, I don't know, pick your choice. There's quite a few of them, right? As I said, I don't know what's going to happen, but I'd give it a 50% chance just because, whatever evidence is out there, and what a lot of clever people I've heard say, that there's something going on, then I would think twice about that switch. And if I was a little devil that didn't want anyone to enjoy heaven, I'd go around and convince people to live forever. So for me, it's really not about living forever. I'll leave the forever for someone else. I'll take my time. But there is another issue here about when you talk about this, can we be eternal? Can we live forever? It's like sending a man to the moon. May not be useful on a daily basis. It's not that each of us hops during lunch break and takes a little peek at the moon. But that effort, that joint scientific effort of many, many scientists, of many people all over the world to try to get to the moon, brought tremendous benefit. It developed so much technology, so many capabilities, that it really gave us kind of a frontier, almost like an ideal to get to. And that ideal, that place we want to be, gives us a choice and gives us a kind of, I'd say, a scientific roadway that we can all get better at. Now, another disturbing fact when you take into account, if you look at expenditure on healthcare, when you really analyze how much money is being spent to treat just the general health, 80% of it is spent on the last 20 years, which really is a bit sad, right? So in that effort of living forever, which is this like common ideal where all scientists can work day and night and make sure we can do it for everyone as well, so it's at a reasonable cost and it's available to everyone. We don't have to reach eternity, but we can really get that last 20 years of life to be an experience that is very positive. So it's really about being young as long as you can until you kind of step out and leave room for someone else. And when we talk about this leaving room for someone else, when you look at mammals in general, you'll see species that have lots and lots and lots of babies or kids, or they have every year 20 offsprings. These are the ones that live a really short life. And those that have lots and lots and lots of them don't really need to live forever. They actually need a little bit of time, and that information, whatever that experience and whatever they've kind of added into their biology, is dissipated along the way. On the other hand, your nice, friendly, everlasting whale, right? Or the kind of species, the mammals, that have very few offspring. These are the ones that actually live longer. And as we, as humans, maybe choose, because we have a choice, to have less children, because they have better chance of living a long, wonderful life, we also have a chance of living a longer life. One last thing before just kind of talking about that issue. When we look at all this tremendous science that has come about in the last decade, and it is from the last decade, enabling so many different modalities of teaching cells how to do what we want them, reprogramming. It is an algorithm, reprogramming them to achieve our physiological goals, whether it's treating disease or just making us younger and healthier or whatever, or happier. Just been a drug approved, by the way, for a neurological condition, making dopamine. So there's many conditions there. When we look at that, we take a cell, and a cell is not just this independent little creature, right? It lives in a society. It has almost like an intelligence that passes through it and makes it aware of its surroundings. It is part of a system. When we have a non-intelligent cell in our body, when we have a really ignorant cell that does not understand it's part of the body, it's called a cancer cell. It's one that does not understand that it is part of society. And, as an information system, that cell, as it kind of combines with all the rest, that's us as part of society. So I'll finish here.
Thank you, Vered. All right, I'm going to briefly introduce the second panelist, and then I'll let you take it away. So Elina Seriva has a PhD in neuroscience and a background in biology, neuroscience, and AI. Her studies have been focused on brain development, regeneration, electrical brain modulation, vision restoration, and more recently on aging as a morphostasis defect and the bioelectricity of aging, and bioelectronic interoperability between conventional and unconventional living systems to uncover deep design principles of biological computation and information processing, making a universal adapter for life. She is a research associate at Harvard Medical School and a staff scientist at Tufts University, working with Michael Levin. She also is a founder of Tiamat Labs, and a deep tech startup company building technological substrate for AGI using live neural tissues, growing your next computer in a dish.
Hi, everyone. Thank you so much for a nice introduction, Matt. So, actually, when we were talking before our panel yesterday, Matt, you mentioned that you did your career journey from computational science to biomedicine. And I'm doing opposite. So for many years, I studied biomedicine, and now I'm trying to move to computer science with my startup in artificial intelligence. And what I know a lot about genes, proteins, and signaling pathways. And what I learned on my way, that biological entities, they are not just hardware, they are not just a bunch of genes and proteins, which are building blocks, but they're highly efficient computational systems with multi-scale competency. And because our audience is mostly artificial intelligence and computer science experts and specialists, I will give an analogy which would resonate with you. So you remember why informational technology revolution happened. So how did we program our computers in 1950s? What we did, we actually rewired our hardware. And how do we program our systems now? We take advantage of software. So we use high-level language to reprogram our hardware. So basically, all this explosion of informational technologies is due to that fact that we moved from hardware to software. And what I think that where biomedicine is today is 1950s of our informational technologies and computer science. It's all about hardware today. We are looking to manipulate genes, proteins, signaling pathways, and we forget about software. That's fine, fabulous, but this is just the beginning. And what I believe, that real revolution in biotechnology, when we will be able to treat diseases and extend our lifespan, will happen only when we find this software and we will learn how to manipulate that. And at this moment, you are probably eager to know what's the software, what software I'm talking about, and I will give you an example. So we all started our life as a single cell, quiescent oocyte, with some gene information inside. And then, through development, we ended up as multicellular organisms with precise anatomy, structure, and function. Our genome in that single oocyte contained information about our building blocks, proteins, but there is no single place in our genome which would instruct what's the body anatomy and structure should be. And it goes to the extent that with some perturbation, this single cell egg can actually separate and give rise to two separate organisms with own mind, intelligence, and independent life. So there is no any place in genome which dictates that two organisms with separate intelligence should emerge. So how it happened that we are not just a bag of cells, but we are so structured and precise in our anatomy? And we think that this is because a very good software level which we have in our body, which is bioelectricity, ancient bioelectricity. And I will give you another example. So I'm a neuroscientist by my background, so I know a lot about brain, and I can give you one-on-one neuroscience course now very briefly. So our brain and generally our nervous system consists of neurons, which are connected to each other. They talk to each other by bioelectricity. So that basically what they transmit from each other is bioelectricity. Our brain sends bioelectrical signals to our muscles or other organs and gets signals from our sensors. This is how our nervous system functions. But before animals at some evolutionary time point got their brains, they didn't have any nervous systems. They were just normal cells. And this communication by bioelectricity didn't appear in evolution all of a sudden. It actually happened that it just evolved to high-speed communication with bioelectricity, but all normal cells in our body, and not only in our body, but in other animals, in plants, and even in bacteria, communicate via ancient bioelectricity. So, and this communication of cells allows them to form this precise structure and anatomy which organisms have. And so what we think that diseases, for example, developmental disorders, or diseases, or cancer, or even aging is happening because cells stop communicating well. Communication, bioelectrical communication between cells becomes fuzzy, not precise, not clean. And what if we could improve this signal-to-noise ratio? What if we could make so that cells would communicate clearly, and by that, they could maintain the precise anatomical structure in the whole organism and function. And so the next step for anti-aging therapies in our understanding would be to learn, to teach, to take advantage of this higher level software, the bioelectricity, and teach organism how to maintain this cellular collective precisely. And I could say something about desirability of anti-aging, but I will let you push back to our software idea.
Awesome. We were discussing on our call yesterday about how you define software versus hardware in life in particular, and like whether you look at like the chemical substrate of cells as a hardware, or is DNA itself more of like, say, a firmware or a hardware, or is it more the things that are etched on, say, a microprocessor versus its atoms? And the idea of controlling the body plan with software I think is fascinating. And one of the things that I thought was the most interesting that came out of your lab with Michael was they could basically radically alter the body plans of things like tadpoles and stuff like that without touching its genetics. And I don't know, you can explain a little bit about what you did and how you're using electricity to manipulate it.
Yeah, so very example. So it's not just some fantasy that bioelectricity can be used as a software of life. We have examples, studies done in Mike's Living Lab. So all I'm talking about, so credentials and acknowledgement should go to Mike Levin and his lab, where I just senior scientist now. Yeah, so we have examples. For instance, there is flat worm called planaria, and with some bioelectric, it's actually immortal, which is pretty interesting. So there is no any thermodynamical reason why biological organisms cannot live forever and be immortal. Yeah, but this is a different question. So planaria is able to regenerate parts of its body. When you just cut it, each half can regenerate its own missing part. And so with some bioelectrical manipulations, you actually can grow planaria which would have two heads. Normally it has just one head, but with some manipulations of bioelectricity, it will have two. And then you cut it again and don't do any manipulations, and each part of planaria will grow exactly two-headed planaria again. So where this information about these two-head planaria is stored, genome is the same. Genes of that planaria are the same. So nothing changed in hardware, but because we manipulated software, the bioelectricity, planaria was able to regrow into headed form again. And then with some bioelectrical manipulations, they were able to return it back. So to cut it, and then it would regrow normal one-headed planaria. Or such example, which would be more interesting for audience probably, it's cancer. As Verit mentioned, that cancer, it's a problem of communication between cells. So one cell, which has own agency, by the way, just decides at some point, oh, I'm not going to contribute in the cellular collective, and I will just, and starts to treat surrounding cells as environment. And this is the problem of not just the, it's the self of it, this cell reduces to single cell organism, but the problem that bioelectrical communication between these cells and surrounding is changing, is impaired. And what Mike's Living Lab was able to do, With some bioelectrical manipulations, again, they are able to remove this cancer in certain animal models. So we have example that it works in cancer. Yeah.
Yeah. So let's see. I think that's we'll start moving towards our discussion part of it now, because keep us on track. But I think these are two things that we touched on today that I think are fascinating. Is this role of information in life, but two sets of information that we have yet to decode or even identify. Like, so we know where the genome is and we can read it, but the genome doesn't contain body plan information. In fact, if I just dropped a gene sequence into someone's lap, that you couldn't look at that and draw a picture of the organism. You couldn't even tell what organism it was if you didn't have a reference for it. And so it doesn't really contain that. So this question of, okay, well, where does the body plan information come from? And how come if I cut off an arm, I don't grow a new one, for that matter? It did it twice already. Or where's the source that needs to be restored? And the other being in the epigenetic landscape about cell fate on an individual level. Where's the master copy of that? We know it degrades and we know it can be manipulated, but where it actually lives in its kind of true or backup original form is a bit of a mystery. And I think this is some of the most exciting stuff in the field. But I guess to kick us off on the question, I'll start with I've read at the core of the topic, how far are we away from achieving viable anti-aging treatments or pushing towards even biological immortality, and what is the path that we need to follow to get there? What's coming forward in the next few years or however long you think it'll take?
So I personally think, when I started the company 10 years ago, 12 years ago, I would go talk to people and tell them, look, you can reprogram cells, you can take a immune cell, you can teach it to fight a cancer, you can teach it to be younger, you can do this. And people would say, yeah. Now, when thousands of people are doing this, right, and it's just obvious you can do all this manipulation, we're at the level where, and I think Elina explained this very well, remember when we went to I remember, tell you how old I am, when I took my little cardboard thing and I put holes in it and I went to the computer room, right? Or where we were computing was 010, like we didn't have high-level languages, right? So that's where we are today in terms of our computational capabilities, okay? We kind of know how to do plus, minus, and very, very simple, basic computational things to ourselves. But you know what's beautiful about biology? It's a language. And what is a language? A language is something where a language is useful when you can express meaning, right? When you take information and you can make that information meaningful. And, when you talk about meaning in information, some people even define consciousness as that. Some people will define to be conscious. What is consciousness? It's the ability to take information and give it meaning. And there's something very deep in that, because when you talk about something being meaningful, you're talking about this being better than that. This is more important for me than that. It's almost that place where you meet free will, right? So there's something very deep about us having that ability to take that biology, which is an information thing, and make that ability to use that information to make a language that is meaningful for us.
It's funny. Sorry, go ahead.
No, I'll just finish this. So we're at the level now that our ability to talk to ourselves is like, toddler language. Like da, da, da. I want this, I want very, very simple language. But with AI coming in and the ability to utilize AI for biological systems, we are going to learn to speak very, very quickly. And I think we're like 10 years away from having that ability to decide how long.
Great. It's funny, coming in to biology from computer science, I never thought I would miss a debugger. We're definitely doing these like punch cards by mail right now. And the marriage of synthetic biology and computer science, I think, are going to be like really big drivers going forward. So I guess I'll pose the same question to you, Elina, about the path and how far we are away. And I'm a little curious also if you think it factors into some of the work you're doing now where you're actually, kind of growing neurons onto artificial substrates. And is this playing a role in it, or is that unrelated?
Yeah, okay. So I will just repeat the message which I've done already, that I believe that true revolution in biotechnology, when we were able to treat diseases and avoid aging, will happen when we take advantage of the software of our body, and this is bioelectrical pattern, the collective intelligence of our cells. Yeah, but then moving forward, let me be a bit futuristic because we're all cosmonauts here. We're talking about biological longevity and biological immortality, but what if we were able to do digital immortality at some point? And as Matt mentioned, I have my startup company, which is focused on building technological substrate for artificial general intelligence. And specifically what we do, we use live neuronal tissues, so-called 3D brain organoids, merge them with electronics, embed in a simulated environment, and make them to do computations. So basically, we are working on creation of new generation of biological computer chips. And we believe that that instead of trying to mimic our brain work in silicon, we actually can take advantage of millions of years of evolution and harness intrinsic capacities of biological tissues to make computations. And yeah, it's possible that this highly efficient computational substrate will be able one day to host our intelligence. And that one day probably we can upload our mind and our identity to that new computational substrate. This is very futuristic.
We have just a few minutes remaining, and I wanted to point out that Vered was planning to be here in person, but she is in Israel, and due to the tragic situation there, she was not able to travel. Vered, I hope you will be able to join us next year. Matt, if you can lead some final comments in the last few minutes here.
So we're going until 45, right? Okay, all right. So I guess we'll do a quick rapid-fire question for the panel, and then I don't know if anyone in the audience has questions, but feel free to line up if you do, and we'll get that next. So the last part of the title here was, should we be doing this? Is it a good idea? And I mean, obviously I'm biased, but I do find an amusing kind of confluence in that pretty much the only thing I can think of that both the healthcare providers, the payers, and the patients agree on is that it's better if you live in really good health for a long time and then die fast. Healthy patients are cheap, sick patients are expensive, dead patients are free. Nobody is really on board trying to live a slow decay for a long time. But I'll throw it to you guys. Vered first, then. Is this something we should be doing? And is there some point where we should stop or just let it ride and see where it takes us?
So, as I said, I'll take my 50% chance on. So let's see what's in the afterlife. And but as a society, should we aspire for that? Yes. And look at Elena's wonderful.
I want to ask you, if you're doing your 50%, what would be the cutoff? If you're at 200, or you're like, okay, I'm done, or is it 300 or like 120? Like, where do you say, you know what, I'd like to see what this whole afterlife has to offer?
Yeah, and it goes back to your ethical question. if I'm kind of switched on forever, is it suicide to switch off, right? I mean, there's a big question there. So how about having a choice, right? That's nice. We like choices. And how about if, I take Elina's wonderful little jar of brain, which is such an old concept, right? I've got my brain in a jar and, it's sort of old thermodynamic kind of, which actually implies, the most viable universe, in physics. It's actually a brain in a jar. And maybe we are a brain in the jar, but we'll find out after I cut off. But
How about you, Elina?
what I am but what I am saying is, I wouldn't worry about that too much now. I think it's a good thing to aspire, because as I said, it puts you on the right path. It puts you on the path of let's be healthy. And it's not about, and let's live a very healthy, long life. As I said, really important in a society, thinking about everyone else living with me.
I want to give Elina a chance to answer this as well.
Yeah, I can give a very briefly complimentary view. So we're all humans, and if we're humans, that means that our goals are likely exceeding our lifespan. We all care about very important things which are longer, far more distant than our own life. And if it's so, we should live longer. We should extend our lifespan to be able to pursue that goals. And I think that we shouldn't worry about immortal people and that we will overcrowd the planet, because I believe that at that moment, then when we will be able to actually extend our life and become immortal, many other options will come, because technologies develop in certain synchrony, and if we are able to live forever, that means that other options will open up, like traveling to different planets, like some new sources of energy and food growth and so on. So I'm quite optimistic about the future.
There's one question from the audience, if you could state it very briefly and a very quick answer.
Sure. Hi, I'm Lisa Girdley, and I'm a program manager. So a lot of the tech talks have been very interesting, but they're not necessarily my day job area of focus. I'm wondering if you had to distill what you do for an explanation for a 5-year-old, how would you describe like your focus on bioelectricity and like just, you mentioned like this ancient history of it, like how would you go about describing that?
Yeah, it's a great question. So I would say that we're looking for software of life and trying to manipulate it so that avoid diseases and increase lifespan.
And Vered?
I would say that I'm trying to make the computational capabilities that we have today available to everyone on the planet. So it's just, just to kind of democratize whatever we have already developed.
Okay, Matt, you get the final word.
So we're trying to manipulate the code of life, and I think I guess to end it, I'd say from the moment humans existed, I think we're effectively predestined to control our genetic fate. That it is, assuming we don't wipe ourselves out first, that the intellectual abilities we have are going to mean that we will manipulate our own genetic code. And if you go forward a bit, humans won't be the same as they used to.
Okay, thank you. What a fascinating panel. Let's give them a hand. Thank you, Vered.
Thank you.